Hi guys, welcome back to the second part of the first lecture on stats in the dyspepsia module. My name's Tom Reeder, and before the break I was talking to you about different types of data, the sorts of data that you might encounter as a pharmacist or indeed any kind of scientist looking at the natural world, recording stuff about that natural world which might be of interest to you. And what we're going to do in this next part of the lecture is look at what we might do with those data. And the first thing that we might do is to try to summarize them so that we can get some idea of what's going on in those data. And we're going to use statistics in order to summarize those data. And that's one of the two key uses of statistics in data analysis. One is for summarizing data, and then in the third part of the lecture we're going to look at the other key use, which is testing ideas about those data. Okay, so if I can get my slides going forward. So the context here really is the question, what are stats for, which is the title of this whole lecture. And I think stats can be quite intimidating as a concept. You might have learnt stats at A level, in which case you might be totally comfortable with them. But for many people, stats are sort of potentially a bit scary, a bit bewildering. They can be used for all kinds of nefarious purposes. We all know politicians love using stats for all kinds of dodgy reasons. But as a pharmacist, you're going to use stats for a really important reason, and that is to make sense of data, because essentially everything we know about how to treat patients, how to dispense drugs, relies on good data. And it's not just data, but being able to interpret those data. And we use stats to do that interpretation. So the first use of stats we're going to look at is how to describe data. And by describing data, a data set might be millions of data points. Making some sense out of those data points, spotting patterns, can be done using descriptive statistics, and often that's what we do. So to illustrate this is actually a poster which my son has on his bedroom wall, and from the distance it looks like just a picture of the Greek letter pi, but if you get a magnifying glass you discover that the entire poster is made of little tiny numbers in two different font colours, and it is indeed the first 6 million digits of the number pi. So I think the sort of point I'm trying to make with this image is, well, A, it's difficult to find nice images for stats lectures, and B, stats is about seeing the pattern in the data. So here we got 6 million numbers, but if we zoom out we start to see a pattern. Obviously a bit of a kind of a silly point, but you'll get the idea as we go along. So I've already introduced a really key word here, which is statistic. So this is a kind of key concept in these lectures. We'll treat a statistic for the purposes of these lectures as a measurable quantity calculated from a sample. And we'll come back to samples later on. And in particular, we're going to look now at a type of statistic called a summary statistic, sometimes called a descriptive statistic. And this is a statistic which we use in order to summarize or describe a data set or a sample. So for example, you'll know the mean, the standard deviation, probably know the mode, the variance. These are all different summary or descriptive statistics which we use to describe what's going on in a data set. So the mean is a really nice one, the average, something that you understand. It tells us something about the typical value in a data set. So if you've got a big pile of numbers, one of the first things you often want to know is, well, yeah, but what's a typical number in this big pile of numbers? And that might be the mean, but it might be the mode or the median. Okay, so we're going to look at the two slightly different scenarios that we encounter when we're looking at data, and that is where we have categorical or quantitative data. So I introduced that major division in the previous section of the lecture. So let's first of all have a look at categorical data, because the kind of descriptive or summary statistics we can generate from categorical data are a little bit different from what we can generate from quantitative data. So the first most obvious thing that you might want to say about really any data set, actually regardless of whether it's categorical or not, is how many data you have. So this is pretty universally referred to as n, sometimes capital N, sometimes lowercase n, but n is the sample size. It's the number of data points that you have available to you. And again, I will come back to what I mean by sample a little bit later on, just to clarify. So in the example data set we're going to look at on this slide, the sample size is 10. There are 10 data points. The example comes from something that's a bit weird. It's this phenomenon called photic sneezing. So some people, when they look at a bright light, or in particular when they look near to the sun, you should never look at the sun obviously, but it works for me even with my eyes closed if I look at the sun. If you look at a bright light, you can trigger a sneeze. And for some people this is really quite violent, but many people have this. I think about a third of people report being photic sneezers. So if we were interested in studying how common this was in the population, we might, and this, if we were in a lecture theatre at this point, I might ask you to put your hand up if you experience photic sneezing. But what we might do is, for each person in a sample, a randomly selected sample of the population, we might classify them as either being a photic sneezer or not. So in my data set here, I've written this down for 10 people, N for no or non-photic sneezer, and S for sneezer, photic sneezer. And I've got 10 people, some of them sneeze, some of them don't. So this is the kind of categorical data set we might quite often deal with in pharmacy and in other branches of science. This is in a sense a kind of symptom which you might want to treat with a drug. And so we can start to say things about this data set rather than just writing out all of the data, if we can generate some summary statistics. So a really simple summary statistic for categorical data would be the frequency of a particular data type, a particular value. And in this case, we're interested in the sneezers. So, well, how many sneezers have we got out of 10? And the answer is 4. Pretty straightforward. We could convert that into a probability. If we picked one of these people at random from the sample, what's the probability that they're a photic sneezer? The answer would be 0.4. So, fair enough. Not earth-shattering. The descriptive or summary stats that you can generate from categorical data tend to be a little bit limited. When we get to look at quantitative data, you'll see that we can start to do some funkier things. So just to say that, of course, stats are not the only way of summarizing data. And actually, for many human beings, the most intuitive way of understanding what's going on, the patterns in a data set, is to visualize the data in a graph of some sort. So with categorical data, you're again a little bit limited in what kinds of graphs that you can generate, but on screen here we've got a couple of classic examples that you'll know about from school. We could generate a pie chart, or we could generate a bar chart. So I'm going to look here at a different example which I'll develop further on the next slide. Let's imagine, since you're pharmacy students, I do apologise, as an ecologist I don't know much about pharmacy, so I have to kind of be a bit imaginative with my examples. So in this case, I'm going to imagine that we are treating patients with snake oil, which is kind of, if you like, a metaphor for dodgy pharmaceutical practices. I actually had a PhD student once who told me that snake oil in their culture was actually a really important treatment. So I didn't certainly not mean to be offensive about this. It's a kind of an idiom in the English language that if somebody's offering snake oil, then they're offering a fake treatment. It's just part of my culture, I suppose. Anyway, doesn't matter for the purposes of this example. Let's imagine that we have taken some patients, some of whom are being given snake oil in order to treat some ailment, and some are not. So at a very basic level, with those categorical data, receiving the snake oil or not, we can draw a pie chart to show graphically what frequency or proportion of the sample are taking the snake oil or are not. Or we could put those in a bar chart, and either way we get some kind of visualization. In this case we can see that more people are being given snake oil than not. So that's all very interesting, but actually the sorts of data sets that we come across are typically more complicated than that. And so one of the obvious things you might be doing if you're looking at patients who are taking a treatment or not taking a treatment is then what the outcomes are for those patients. So we might look at whether or not these patients are hospitalized with the condition that's being treated. So we could say, well, for every patient that's been given snake oil, were they hospitalized or not? For every patient that was not given snake oil, were they hospitalized or not? We end up with a slightly more complicated data set immediately. So now we've got 4 possible combinations, snake oil or not, hospitalized or not. And we can draw up a table of these frequencies, which is another really useful way of summarizing categorical data. In this case, now allowing us to summarize 2 variables, so the treatment and the hospitalization, simultaneously in what we call a cross-tabulation. And for a 2-way cross-tabulation like this, where there are 2 variables at play, the treatment and the hospitalization, that's a special kind of cross-tabulation called a contingency table. So there is a bit of jargon involved in stats, but it is worth knowing that when you see this kind of table showing you the cross-tabulation of two different variables against each other, where the variables are categorical, so you have frequencies in each possible combination, then you're dealing with what's called a contingency table. And later on in the second lecture, we'll look at a statistical test that allows us to ask, in this case, whether patients who've been given snake oil were more likely to be hospitalised than patients who weren't, or vice versa. Okay, so what about quantitative data? Things get a bit more interesting because you can do quite a lot more with quantitative data, where the data are collected on a numerical scale of some sort. There are really two kinds of summary statistics that we can generate for quantitative data. We can generate what we call location data, or sometimes called measures of central tendency, or we can generate measures of spread or dispersion or variability. So essentially what we're talking about here with location data, location statistics, is what's the typical or central or most common value in a data set, or the average value in a data set. Whereas when we're looking at spread, we're thinking about, well, how variable are the values in the data set? How far is a typical value or a randomly extracted data point from the average or the center of the data set? So those two properties are really important when you're thinking about a data set. You know, what are most individuals like, and how variable are individuals? Are they hugely variable, or is everybody, or everything, every organism, every bacterium, every petri dish, every test tube about the same? So that's what location and spread are going to do for us. And if you'll excuse me, at least for this one example, I'm going to use an ecological example because it's close to my heart, and it's actually the one that I used to teach the biologists, and I thought, well, you can live with a little bit of ecology just because it allows me to tell you a bit of a story. So we're going to look at some quantitative data. These are discrete data, so they come in integer values, from a PhD student of mine called Jessica, who's actually in that photograph there. That's Jessica kneeling down in front of her Land Rover, and she's actually counting feces, which is one of the sorts of attractive jobs that ecologists get to do in the field. Luckily for her, this is in Botswana, so it's a pretty exciting place to do poo counting if you're going to count feces. And in fact, she was studying the interactions between hyenas and lions and other large carnivores, looking at competition between these species, and in particular looking at how they interact with each other through latrines. So hyenas produce latrines, piles of feces, and these are important signalling posts for communicating with other hyenas, and also communicating with lions and leopards and things like that. So that's all irrelevant for the purposes of my example. I'm afraid when you're a statistician, all you're interested in is the numbers. So Jessica in this study is generating integer value quantitative discrete data, and each latrine that she visits, each pile of feces that she visits, generates a number telling her how big that latrine is. So here are the data down here. We've got 4 in the first, 4 feces or poos in the first latrine, then 2, then 0, then 4, then 3, then 0. And in fact, she was monitoring these over a period of time, so she was going back and counting them again and again. So we've got some numbers. We can now start to say something about these latrines in general using summary statistics. And really the most obvious thing that we might want to do is to calculate the location of these data, as we call it. So in other words, the sort of middle of the data set. And the most obvious way of doing that is to use the mean. And you all know how to calculate a mean. It's in mathematical notation, it looks a little bit frightening, but actually it's a really straightforward calculation. What we've got here is this Greek letter sigma, which means sum or add up all of these values of x between I equals the first value and I equals the nth value. Remember, n is the sample size, so in this case we've got 20 latrines, 20 data points, so n equals 20. So there are going to be 20 values from the first value to the 20th value that we need to add up in order to then divide through by the sample size and calculate the average number of feces per latrine, which in this case is 3. If you do the maths with this particular data set, you'll find that if you add up all of the feces in all of the latrines, divide through by 20, and you get 3. So that in stats terminology is, or in stats sort of notation, is indicated by x. If x is your variable, x with a little bar above it, and the bar represents the mean or the average of that variable x. So in our case, the average value of X from a sample size of 20 is 3 feces per latrine. Brilliant. So you're also probably familiar with other measures of location, other measures of central tendency in a data set. So you'll know that these can have different uses in slightly different contexts, but basically they all tell you roughly the same thing. They tell you about where the center of a data set is. The perhaps second most commonly used measure of location after the average or the mean is the median. And the median is the central value when you put the data in rank order. So here I've put my latrine data in rank order from those latrines that actually had no feces through to the biggest one which had 11. And the central value, well, in fact, in this case, because there are 20 data points in total, there are 2 central values in the middle of the data set, both of which are 2. So to calculate the median when you have more than one number in the middle of the data set, because you've got an even sample size, you just take the average of those 2 data points. So in our case, obviously that's 2. So the median number of feces per latrine is 2, which is slightly different from the mean, which was 3. And if you think about it, you can see why the mean is higher. It's because we've got a couple of really big latrines up here, which are sort of having a disproportionate effect on the average or the mean. Whereas the median is perhaps telling us, in a way, something a little bit more representative about the sort of typical size of latrine in Jessica's study. The third measure of location that you will have come across is called the mode, and the mode is just the most common value in a data set, and the mode is probably the least useful of the measures of location, but we do come across it now and again. It's only useful for discrete data, obviously, because if you've got continuous data on a sort of infinite scale, then there isn't really going to be a commonest value. But for discrete data, like our set here, I've sort of grouped them together to show you that the commonest latrine size in Jessica's study was 2 feces. So it's the same as the median, but slightly different from the mean. Jolly good. Okay, so that's location. What about spread? Spread is this idea of variability. How much variability is there in the data set? The simplest thing that you can say about spread in a data set is to give the range, the difference between the maximum value and the minimum value, which in our case is 11. If you take the biggest latrine and the smallest latrine, the difference is 11 feces. So that's the range. That can be useful. We could extend the idea of the range to look at things called quartiles. So the range gives you the upper and lower limits of the data set. The quartiles are what you need in order to divide the data set into 4 quarters, hence the name. So if the median is the middle of the data set, that's this dotted line here, that divides the data into 2. If we want to divide them into 4, then we're going to need a lower quartile and an upper quartile in the data set so that we get 4 equal chunks of data. So you can calculate those just as you would calculate the median. So in our case, they would be the average of these 2 values, which is 1, and the average of these 2 values, which is 4. And you can express those in various different ways. You can put them on a graph as well, which is quite useful. And they tell you something about the spread of the data, not just the maximum and minimum values now, but something about sort of the distribution of the data across the possible values in the data set. In a moment, we'll see what that looks like on a graph. Once you've got your quartiles, you can tell your readers or your assessors something else interesting about the spread of the data, which is the interquartile range. So that's the difference between the first and the third quartile, sorry, the upper and the lower quartile, which is a way of expressing the spread of the data set, ignoring the extreme values, because the range obviously takes into account the extreme values. The interquartile range kind of cuts those off and ignores them and says, well, how variable is the bulk of the data, the middle of the data set? And that's the interquartile range. Other measures of spread that you probably have come across include the standard deviation. This is quite a clever one. This is the average difference between a given data point and the mean or the average. So what we do is we calculate the average, x bar, and then we look at the difference between each individual data point and x bar, and then we work out the average of those, and that's the standard deviation effectively. So in my case, here's a couple of examples. Here are the data again. We've got the first data point here, which is 4 feces, and then this one over here, which is 0, and we know the mean is 3. So the difference between the mean and the first data point down here is just 1, whereas the difference here for this data point is -3. So we get these differences, or they're sometimes called deviates, that's x minus x bar, and we use them to calculate an average size of the deviation, and that's going to be the standard deviation. So in order to do that, the first thing we have to do, like whenever you're calculating any kind of average, is to add them all up. So we are going to take these differences, x minus x bar, and we're going to calculate that for every single data point in the data set. So there's 20 of them, using the sum sign again. So we're summing all of these differences, but we got a problem. If we add them all up just like this, here's a +1 and here's a -3, what you'll find is half the data points roughly are going to be above the mean and half are going to be below the mean. So you'll end up with half your numbers, your differences, being negative and half of them being positive. So if you add them all up, the negatives will cancel out the positives and you'll end up with about 0. So when we're trying to add up the total amount of variation in the data set, we square these differences before we add them up, giving us something called the sum of squares. So we take the difference between the mean and the data point, we square it, and what that does, of course, is it gets rid of the minus sign. If you square a negative number, it's going to be positive. And then you add all of those up, and you end up with this thing called the sum of squares, which is the total amount of variability in the data set. And remember, the objective here was to calculate the standard deviation. Now, the standard deviation is the average difference, not the total amount, but the sum of the differences. So to calculate an average, what do? Well, you divide it through by the sample size. So that's what you do with the sum of squares. You take the sum of squares, you divide it through by the sample size. Now, for obscure statistical reasons that you really don't need to worry about, that is corrected by -1. I don't really know why myself, actually, but the principle here is you're taking the total amount of difference between each data point and the mean squared, dividing it through by the number of data points you got to give you an idea of the average squared difference between a data point and the mean, and this is called the variance. So the keen-eyed amongst you will have spotted that this is not the standard deviation yet. Why not? Because this variance is expressing these differences as a square, because we've squared each difference, so we made them a lot bigger than they really are. If the difference was -3, we've squared it, and now we've got 9. So we've added them up across the whole data set and ended up with this really big sum of squares, which we divide through by the sample size, and it's still a big number. That's the variance. So what do? We take the square root of the variance, and that is the standard deviation, because now it's expressed in the right kinds of units. It's going to be expressed on the right scale. So the standard deviation is the average size of the difference between a data point and the mean, with the sort of twist that we had to square those differences in order to get rid of the minus sign, and this funny little statistical fudge of a -1 that you don't really need to worry about, but it just pops up in the equation for the standard deviation, which looks like this. So a slightly scary looking equation, but really all it's saying is what's the average difference between a data point and the mean, and that is a really useful measure of spread. So how do you represent these properties of quantitative data graphically, the location and the spread? One of the best ways to do it is using a frequency histogram. So this is a sort of hypothetical example of how many paracetamol tablets are kept at home by a whole load of people that we've sampled, and we find that most people have got at least some paracetamol. In fact, the sort of typical value looks like it's about 15 to 19 kept in anybody's medicine cabinet at any one time. And there's even a few people who've got vast hoards of paracetamol. Perhaps these are people who are being treated for a long-term illness or something like that. And by plotting it like this as a frequency histogram with the frequency up the side and the values of the variables put into bins on the x-axis, we get a really nice idea, not just of where the middle of the data set is over here, this is the median, but also the sort of spread that there is in the data. In this case, we've got really quite a lot of spread with a few very big values up here. Another way to plot out these properties, the location and spread of the data set, is to use a box and whisker plot. So here we've got a box and whisker plot. I mean, normally this would be part of a larger graph, but I'm just homing in on an individual box with these whiskers just to show you what all of this means. The whiskers represent the bottom and top values, the upper and lower range, upper and lower extent of the range of the data set. So the difference between the upper and the lower is the range. The heavy bar in the middle represents the median or the midpoint of the data set. And then we use the box around the median to represent the upper and lower quartiles, so that the difference or the size of that box represents the interquartile range. And so here we've got a neat way of representing all of that information, the range, the interquartile range, and the location of the median, all in one simple box and whisker. So this is how we actually use it in reality. We've got an example here of how much caffeine there is in different servings of a whole range of different drinks. And these are actually, I think, real data. So what you find is that generally coffee, filter coffee and espresso here, have a lot of caffeine in them, unsurprisingly. But filter coffee is very variable. So you get some filter coffee that's got relatively little caffeine and some that's got a huge amount. Whereas, say, Coca-Cola down here, it's got some caffeine in it, but it's got a really tight interquartile range, showing you that the manufacturing process for Coke means that the amount of caffeine that you get in each serving is really tightly controlled. So there's very low variability, very low spread compared with the filter coffee. So looking at the median as a measure of location and the whiskers and the box as a measure of spread gives you a really nice way of comparing different data sets. Okay, so that's enough about summarizing data and descriptive statistics. In the final part of this lecture, after the break, I'm going to talk to you about how to use stats to test ideas. So I will see you shortly.